A 6.0 Newton force is applied horizontally to a 2,691 gram book that is sitting on a table. The force of friction has been determined to be 3.2 newtons. Determine the magnitude of all the forces and the acceleration of the book. So after reading the problem through, I've identified the givens that were stated in the problem. We know that the mass of the book is 2,691 grams. The force applied to the book, 6.0 newtons, and the force of friction as 3.2 newtons. Again, for a visual demonstration, we have a 6 Newton force applied to your positive x direction, causing this book to accelerate with a force of friction, 3.2 newtons, acting in the opposite direction. Now, after you've identified the known variables, the next thing you do is actually draw out the free body diagram. See if you can try and do this on your own. Alright, so we have our force of gravity acting straight down on the book towards the center of the earth, the normal force from the table pushing back up, supporting it. We have the force applied pushing us in the positive x direction, and the force friction is opposing that. So we've identified all our variables. Notice that I know that the object is not accelerating in the vertical direction. I've drawn these vector arrows to be equal in length, indicating the magnitudes are the same but opposite in direction. And the force applied is 6 versus the 3, so it's roughly twice the size of the force of friction. Now, this point, now that you've identified all the forces on your free body diagram, you want to go ahead and apply Newton's second law. The sum of the forces is equal to the mass times the acceleration. And in doing so, we have to actually do it one step at a time, in one direction at a time. We can't sum up all the forces. Just like when we were projectiles, when we were analyzing things in vertical and horizontal, we're going to be breaking down the forces. In this case, everything is already in either a horizontal or vertical orientation. So we need to find all the magnitudes of all the forces. So why don't we start with the vertical direction. Alright, so the sum of the forces is going to, in the y direction, or the vertical direction, is going to equal the mass times the acceleration in the y direction. And when you're looking at the forces, we have the force normal going up, and we have the force of gravity going down. So we're going to apply our frame of reference that up is positive and down is negative. And so the way that I'm going to do this is I'm actually going to sum the forces. So what we're going to do is sum up the forces in the vertical direction, and when I look at this, force normal is positive, is in the positive up direction, minus the force of gravity is equal to the mass times the acceleration in the y. Well, the acceleration in the vertical is 0, so therefore this whole side of the equation goes away and becomes 0. I can add the force of gravity to both sides, and I know that the magnitude of the force normal is equal to the magnitude of the force gravity. In this particular case, as I said before, that's not always going to be the case. It's going to be a function of all the forces that are acting in the vertical direction. Initially, oftentimes the force normal is going to be supported and counteracting and equal to the force of gravity. But just be mindful that it's not always the case. You have to go through the process of summing the forces in the vertical direction. Now, I have an equation for the force of gravity. It's the mass times the acceleration due to gravity. So I need to just go ahead and solve for the force due to gravity. And that is 2.691 kilograms times 9.8 meters per second squared. Now, we were told that the book was given to us in 2,691 grams. So I went ahead and converted it. Unit cancellation of 1,000 grams of 1 kilogram will give me 2.691 kilograms for the mass of this book. Plugging into our calculator, we found that the force of gravity is 26.3718 newtons, and therefore the force normal is also 26.3718 newtons. Now, so I've identified two different magnitudes of the other two forces. We were actually given the other two forces, the force of friction and the force applied. So at this point, we can go ahead and sum the forces in the horizontal to determine the actual acceleration the book experienced. So summing the forces in the horizontal is equal to the actual summation of the forces is equal to the mass times the acceleration in the horizontal. So the sum of the forces in the horizontal is going to be the force applied in the positive x direction or positive horizontal direction minus the force of friction. Again, the force of friction is minus when we're adding it together because it's really like adding a negative force vector. We can just go ahead and subtract it. I can say the force applied plus the force of friction if the force of friction is negative, therefore it is just minus the force of friction. So that all together sum up is going to equal to the mass times the acceleration in the horizontal. We're trying to solve for the horizontal acceleration, so I can divide both sides by the mass and I end up with an equation for the acceleration in the horizontal or x direction as being the force applied minus the force of friction divided by the mass. Plugging in, we find that 6 newtons minus 3.2 newtons divided by 2.691 kilograms is going to give me a horizontal acceleration of 1.0405 and change meters per second squared, or with two significant figures, 1.0 meters per second squared. Don't forget, the units are going to be a little funny for you at first. We got newtons divided by kilograms. How is it that we ended up with meters per second squared? Well, let's take a look at that. We know that a newton is a kilogram meter per second squared. So on the top here we have kilogram meter per second squared all over kilograms. So the kilograms actually cancel out and what we're left with is just meters per second squared for our units for the acceleration. Thank you, and I'll see you soon.